So in this video, I'm going to run through the answers to the reaction questions in exercise 1 of 25.2. So there are questions 12 and 13. In question 12, I just ask you for the products, but in question 13, I ask you for the mechanism for A, B, and C. So as I do the products for A, B, and C, I'm going to also do the full mechanism. So I'm starting off with benzene, I'm reacting with bromine, and I'm doing this in the presence of a halogen carrier catalyst, iron bromide. Benzene is your nucleophile, which means what it's reacting with, bromine, that is going to be your electrophile. Okay, but benzene is not a very good nucleophile. The electrons are delocalized, they're spread out, and that makes it less effective at attracting and polarizing an electrophile. So because benzene is not a very good nucleophile, we need to make the electrophile really, really good. And that's why we use the catalyst. So in the first step, you take your electrophile, you react it with your catalyst, and you generate an even better electrophile. So we know to be a good electrophile, you want a delta positive charge or ideally a positive charge. At the moment, your Br2 only has a delta positive charge. By reacting it with the catalyst, we end up forming something with an actual positive charge. So you end up forming Br with a positive charge, and you form FeBr4 minus. Okay, so now I'm generating something with a positive charge, much more reactive than what I started with. Now that I've got a good electrophile, I will be able to react it with benzene. So I'm drawing out my benzene and I'm drawing out my bromine with a positive charge. Benzene is my electrophile, which means my curly arrow is going to start with benzene. I need to start it here on the pi electrons. It's going to reach out and it's going to attack the bromine. When this happens, you get the following intermediates, okay? So I can put bromine on any carbon. They're all equivalent. I'm just going to put it here at the top, okay? They're all equivalent because there are no other substituents on benzene, okay? If there was, they wouldn't be equivalent, but in this case, it doesn't matter where you put your bromine, okay? If I start off with a positive charge, I'm still going to have a positive charge here, but instead of being on the bromine, it's now going to be in the benzene ring because both of the electrons in this new bond are coming from benzene. Benzene is effectively losing an electron. It's not on any one carbon atom, though. That positive charge is shared, and because it's shared, I draw this as my intermediate, okay? Your semicircle should be pointing towards your new bromine, and then I've got a positive charge. This is going to be a substitution mechanism, which means the hydrogen on the carbon that you've just added the bromine to is going to be removed. So the bromine comes in and takes the hydrogen's place. The two electrons that are in this carbon-hydrogen bond go back into the ring to reform the delocalized system. Remember, the delocalized system offers stability, which is why it's favorable to form it. So I'm losing that hydrogen, but the bromine remains. Because both of the electrons in that bond go into the benzene ring, hydrogen leaves with no electrons at all, so hydrogen leaves as a H+. In your third step, you regenerate your catalyst. So our original catalyst was FeBr3. I have to show that that catalyst forms again. I take my H+, I react it with my FeBr4 minus, and I end up, sorry, that's Br4, and I end up with FeBr3, so I'm regenerating my catalyst, and I also end up with hydrogen bromide. Step 1, 2, and 3, this whole mechanism is worth 5 marks. You need to detail each of those steps. The next mechanism is going to be quite similar. Again, I've got benzene. This is my nucleophile, which means over here I must have an electrophile. This carbon here is going to be your electrophile. It's bonded to an electronegative chlorine and a more electronegative oxygen, so this carbon here is your electrophile. Even though it's bonded to two electronegative atoms and has a delta positive charge, it's still not a great electrophile. It's pretty good, but we're going to make it even better by reacting our electrophile with a halogen carrier catalyst. And again, the reason it has to be such an amazing electrophile is because benzene is quite a poor nucleophile because of those delocalized electrons. So I'm going to take my acyl chloride, and we do study acyl chlorides in more detail in chapter 26. I'm going to react it with my halogen carrier catalyst, and the same thing is going to happen as above. My halogen carrier catalyst is going to pick up the halogen, so that chlorine is going to be removed, It picks up the halogen and I end up with AlCl4 minus, and this carbon ends up with a positive charge. So it's gone from being delta positive to fully positive. It is now a better electrophile, and it is now able to react with our poor nucleophile. It's able to react with benzene. So I draw out my benzene ring. I draw out my electrophile. Again, benzene is my nucleophile, so my arrow is going to start with benzene. It's going to end on my electrophile. And when it does that, okay, look at where I'm forming the bond from. It's from the carbon, from the benzene ring to the carbon that's bonded to the double bond. So I need to draw this carbon here is bonded to 2 other carbons, 1, 2. And this carbon here is also double bonded to an oxygen, okay? So just make sure you're drawing that correctly. You're drawing a bond between the benzene and this carbon here. This carbon is bonded to 1, 2 other carbons and is double bonded to an oxygen. So again, I'm initially going to form an intermediate. That positive charge doesn't just disappear, but it's now with the benzene, as both electrons are coming from the benzene in this new bond. Again, when I'm drawing my semicircle, I'm drawing it pointing towards my new substituent, and I'm putting the positive charge there. That shows that that positive charge is being shared around the ring. Again, I'm going to have a substitution reaction, which means the hydrogen that's on that carbon that's just got the new substituent is going to be lost. The electrons that in that carbon-hydrogen bond are going to go back into the ring. And when they do, because both electrons stay with the ring, hydrogen leaves with no electrons at all, and it leaves as a H+. Sorry, I'm drawing an arrow. So I end up with H+, and I end up with my product. So the ring reforms, and then I've still got my new substituent. The last thing I would need to do is show the regeneration of my catalyst. So just like in the reaction above, I take my H+, I take my AlCl4-, I end up back with my AlCl3, so I'm regenerating my original catalyst, and I also form hydrogen chloride. The next one, C, this is the nitration of benzene. Again, benzene is my nucleophile. It will always be my nucleophile, which means this must be my electrophile. Again, not a very good electrophile, so I'm going to react it with a catalyst to generate an even better one. HNO3, I react it with H2SO4, and this equation you are just going to have to learn, okay? You end up with an NO2 with a positive charge, and that's going to be your electrophile going forward. You end up with HSO4-, so you can see you've lost a hydrogen and 1 oxygen from HNO3, and you've lost 1 hydrogen from H2SO4. So the hydrogen and the oxygen and the other hydrogen combine to form H2O, and that's an equation you're going to have to learn. But now I've generated a really good nucleophile, NO2+. So once I've got my really good electrophile, I can react it with my benzene ring. Okay, that positive charge is on the nitrogen. You're forming a bond between benzene and nitrogen, not benzene and oxygen. So I'm going to draw my arrow to my nitrogen. This time I'm going to put my new substituent all the way down here, and then I can put it on any carbon, okay? And when I'm drawing my intermediate, I'm going to have my semicircle facing where my new substituent is, again with that positive charge. I lose the hydrogen as a substitution reaction. The electrons from that bond go back into the ring. That means I reform my my benzene ring, and I'm losing a H+. And just like in the mechanisms I've just gone through, in step 3, that H+ is going to combine up here with my HSO4-. And when it does that, I end up with H2SO4. I regenerate my catalyst. So for the rest of these, I'm just going to draw the products. I'm going to use the same approach every single time. Benzene is my nucleophile. I need to find an electrophile. The carbon bonded to the bromine is delta positive. That makes it my electrophile, which means my benzene is going to be attacking that carbon there. You're not asked for mechanism. You don't need to draw arrows or dipoles, but it helps you see where your product is going to be. So I'm going to be drawing my benzene. I know it's substitution, so my benzene ring is going to be intact. I'm going to be bonding my benzene ring to this carbon right here. This carbon is bonded to a carbon, which is bonded to two other carbons. So there it is, drawn to the carbon, which is bonded to two other carbons. It is originally bonded to a bromine, but this carbon cannot have four bonds, and it's the bromine, carbon-bromine bond that is going to break when benzene attacks. So I'm losing my bromine and I'm left with 1, 2, 3, 4 carbons, and here I've got 1, 2, 3, 4 carbons bonded to my benzene ring. In the next one, I don't have a benzene, I've just got an alkene, but again, it's going to be my nucleophile, and if I were to draw out my hydrogen bromide, I'd have a delta positive on the hydrogen, a delta negative on the bromine, and my alkene is going to be attacking that hydrogen. Alkenes do not undergo substitution reactions, however, they undergo addition reactions. You end up adding the hydrogen and the bromine to the two carbons that were originally part of the double bond. Next one, again, benzene is my nucleophile, and my electrophile is going to be here. That carbon right there, that's bonded to the chlorine and the oxygen. Again, I need a catalyst to drive this reaction forward because benzene is such a poor nucleophile. Again, it's going to be substitution, so I'm going to be reforming my ring. Doesn't matter where I put this, I'm just going to put it here. It's going to be bonding to this carbon right here. Okay, and that carbon is bonded to that carbon is bonded to another carbon, and this carbon here is bonded like that. The carbon here is also double bonded to an oxygen. It was originally bonded to a chlorine, but again, you need to break one of the old bonds in order to form a new. This carbon has 4 bonds. To form a new bond, one of those bonds must break, and it's going to be the carbon-halogen bond, again, just like it was above. Next question, I asked you for the reagent. Okay, so you've got benzene. You can see that you're adding an alkyl group. So you need to suggest a reagent. That alkyl group has got 1, 2, 3 carbons in a chain, and there are 2 carbons coming off carbon number 2. So I'm just going to draw that for myself. Okay. However, this alkyl portion alone would not react with benzene. Okay. If you look in your notes for the alkylation of benzene, which is what we've got here, you'll see you don't start with an alkane, you start with a haloalkane. And it doesn't matter which halogen you choose. I'm going to choose chlorine, okay? But the carbon, which I've labeled as carbon 1, that ends up bonded to the benzene, that carbon has to be bonded to a halogen, chlorine or bromine, and I've chosen chlorine. As well, you need a catalyst. So because I've used chlorine, I'm going to use aluminium chloride. I could also use iron chloride, okay? But if I've chosen chlorine as my haloalkane, I need to have a catalyst that also contains chlorine. In the next reaction, you see I've got the nitration of benzene. Again, you need to know the conditions. So HNO3, nitric acid, and then I also use concentrated H2SO4. That concentrated is important. You do need to mention that it's concentrated sulfuric acid that you are using. You're also using concentrated nitric acid. You should also include that. And this one here looks complicated. I appreciate that, okay? But I've got benzene reacting with something to form this, okay? So I need 1 carbon bonded to an oxygen that's bonded to another carbon that's bonded to another carbon. So I'm going to draw that for myself. I'm going to draw what I've got. That's new. Dun, 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 dun. Okay, so I need to add this. Again, this carbon here, in the product, you can see it's got 1, 2, 3, 4 bonds. What I've drawn at the moment, I've only got 3 bonds. So that carbon must have originally been bonded to something else. And just like what we've seen above, it would be bonded to a chlorine. Okay, if that was the carbon that ended up reacting, it must have had something electronegative on it to make it susceptible to attack by benzene. So that's going to be a chlorine. And again, you're going to need a halogen carrier catalyst. And again, because I'm using chlorine, I'm going to use AlCl3. These types of reaction questions, they do take a little bit of practice, but they are very important. You always get questions on benzene, the reactions of benzene, especially those mechanisms which are worth 5 marks, and they really are worth your time. So the last question I wanted to go through is question 14, where you're asked to compare the reactions of butadiene and benzene with bromine. when you are answering this question, you are told you need to write a mechanism, but even if you weren't, rather than trying to describe the reactions in words, draw your mechanism. It's far easier and you're far less likely to make a mistake if you just draw the mechanism rather than trying to explain everything in words. So all I've written here is that butadiene reacts with bromine without a catalyst, and I've given the name of the reaction type, electrophilic addition. Other than that, I've just written out the mechanism. I'm not trying to describe in words what's happening. You don't need to. This will get you all of your marks and it's easier. Underneath then, I say that with benzene, you do need a halogen carrier catalyst, and I've given an example, and it's electrophilic substitution. And again, I've written out the mechanism. So you'll notice that I didn't include steps 1 and 3. I've just focused on step 2 because step 2 is the actual reaction mechanism. You could include 1 and 3 if you like, but that alone as a question is worth 5 marks. This is a 6-mark question that incorporates all of these other elements. So just including this is all that's going to be required, just showing the actual reaction between benzene and the electrophile. And then you're asked to comment on why alkenes are more reactive. So it doesn't need a catalyst, it is more reactive. You're asked about why, and there's specific things that you need to say, and this is straight from the specification. The reason alkenes are more reactive is because the electron density is localized. That's how you should describe it. So the electron density of the pi bond is localized. Because it's localized, because you've got the electrons in a smaller area, you've got this area of high negative charge, and that is sufficient to attract and polarize your electrophile. So by polarize, remember bromine, it doesn't have a permanent dipole, but if the bromine were to approach the electrons in that pi bond, the electrons in the pi bond would repel the electrons in the bromine-bromine bond and would create a dipole. So that's what I mean by polarize. That's the exact language from the spec. That's what you should be saying. And then you're talking about benzene does require a catalyst because you're saying the opposite. Instead of saying localized electron density, you're saying delocalized electron density of the pi ring system. So basically the electrons are more spread out. Because they're more spread out, they're less effective at attracting and polarizing bromine, and that's why you need a catalyst. You use the catalyst to create a better electrophile because benzene isn't capable of doing that. And then I also had a final little point here. I've mentioned above that alkenes undergo addition, whereas benzene undergoes substitution. I've just put a point at the end to explain why. The substitution maintains the delocalized pi ring, and that makes benzene more stable. Okay, so that's all you would need to say to answer those questions. Make sure you know your mechanisms, and the underlined terms are going to be key.